All right. Hello, everybody. Welcome back to another live stream. Hello, Mr. Bones. I am so ready for this as well. How's it going, everybody? Just a chill. Which day it is actually? Today is just a chill Wednesday evening here. Hopefully, you're doing fine. Me personally, I cannot complain. Just grinding all day. You know, all the same stuff. So, yeah. Doing alright, great. So guys, you know that I've been doing some embedded Rust lately, and yeah, we have a whole series on this now on this channel. Like, this playlist is just like building this guitar project. But what I realized is I never like took my time actually and read some resources, which is a bit of a shame. But do you actually need them? Probably you need them. So here today we're just gonna take a look at some resources, try to learn some stuff, maybe do some experiments. I don't know. We'll see how this thing goes. I have some resources already. Mainly we're gonna just take a look at the ESPRS book and whatever else that we can find on the internet. I'll read along. Yeah, hopefully. Yeah, I don't know like which format I'm gonna use here. Like, I think I'll just like read aloud and just like skip some sections, or I don't know. Like, we'll see. Maybe I'll do some experiments with the boards that I have. But just to give you the reasoning for this live stream is because, yeah, I'm doing a lot of embedded stuff. I need to be I need more knowledge about these things, first of all, and secondly, I will be I'm like kind of active in the embedded Rust scene now. So yeah, maybe I'll give some talks or like do some workshops. So I need some proper knowledge, because if somebody asks, hey, what is this HAL library, what am I gonna say, you know? So there you have it. This is why we are here today. Let's just dive into it. ChatGPT. No, we're not gonna dive into ChatGPT. So there's this STD training thing. This is from ESPRS. I think I'm just gonna go ahead with this this page. I don't know where else. So there you go. You can just like follow along, or you can just save it for later. But you know, I'm just like freestyling here. Okay, so if you're curious about a certain topic, if you want me to dive into a certain topic, just stop me. Just gonna do it on my pace here. So yeah, there you have it. So Espressive, this company was making the ESP chips and boards or whatever. So there you go. So introduction. The goal of this book to provide a comprehensive guide on using the Rust programming language with Espressive devices. So Rust embedded. Maybe we should start from that. This is too specific to Espressive, like ASP32. So let me actually go ahead and start from this. This seems more like a more general thing. I'm mostly learning cyber Rust stuff right now. Cool, man. Nice. You might build some toys for those stuff, you know. So, alright, the Embedded Rust book, introduction. Welcome to the Embedded Rust book, an introductory book about using the Rust program language on bare metal embedded systems such as microcontrollers. So bare metal means no STD, I'm guessing. So yeah, embedded Rust is everyone who wants to embedded programming while taking advantage of the high level concepts and safety guarantees of the Rust language provides. Alright, scope. Get developers up to speed with embedded Rust development, how to set up a development environment, share current best practices about using Rust for embedded development, how to best use Rust language features to write more correct embedded software. Nice. I am very interested in this because, you know, I have this embedded project. I'm gonna learn a lot from this probably, hopefully. Wish I knew that for my robotics classes. Yeah, dude. It's like Rust is for everything, you know. So as a cookbook in some cases, how do I mix C and Rust in a single project? Hopefully I won't need that. This book tries to be as general as possible, but make things easier for both the readers and the writers. It uses the ARM Cortex-M architecture in all its examples. However, the book doesn't assume that readers familiar with this particular architecture and explains details particular to this architecture where required. Alright, so we're using this ARM Cortex-M. Who is this book for? People with either some embedded background or some Rust background. For those without any prior knowledge, we suggest you read the assumptions and prerequisites to catch up on missing knowledge. Okay, so what do we need? You're comfortable using the Rust programming language. You have written, run and debugged Rust applications on a desktop environment. You should also be familiar with the idioms of the 2018 edition. Okay, I'm kind of familiar with that. Comfortable developing, debugging embedded systems in other languages such as C, C++, ADA. Well, yeah, cross-compilation, memory mapped peripherals, interrupts, common interfaces such as I2C, SPI, serial. Alright, so let's get a quick summary on those things. Guys, we have ChatGPT over here. Just yeah, let's do the give me a quick summary on these things. There you go. Yeah, we're just like completing the prerequisites at this point. So real. Writing code on okay, cross compilation. I know what that is. I'm just gonna skip that. Memory mapped peripherals. Many microcontrollers expose hardware registers as special memory addresses. Okay, instead of special instructions, you read write to those addresses as if they were normal variables in RAM. Example: writing a value to my toggle GPIO pin provides direct low-level control over hardware. Interesting. I didn't know about this. I never used something like this. Interrupts, yeah, mechanism that lets hardware or software temporarily interrupt the CPU to handle an event immediately. A button press. Alright, that's easy. Alright, common interfaces. I2C, inter-integrated circuit. Alright, I heard of this a lot, but I don't know what this is. Two-wire bus, SDA for data, SCL for clock, used for sensors, EEPROMs, displays, master slave, moderate speed, short distances. That is not clear to me. SPI, serial peripheral interface, 4 wires, faster than I2C, often used for displays, SD cards. Okay, I think I got it. So guys, I'm gonna give you an example. If you're not familiar with any of these things, it's not actually complicated. So SPI, MOSI, MISO, SDKCS. So what is SPI? I'm gonna just show you. You see those 4 pins right here in this display? Those are like the control pins, and this is using SPI. And boom, yeah, that's what it is. We don't need to make it complicated. That's just a protocol. Serial peripheral interface. Okay, I'm gonna put this back in. I'm using SPI for my project as well. But like, in case you don't know, I have this thing. Yeah, using SPI to show stuff on the screen. All right, I'm gonna put this away. Let's continue. So I2C, I don't think I'm using this. I don't know. I never used this, I guess. Let me do a quick search on this. I2C Rust. SPI be faster. Yeah, I think it's faster. I2C Rust for interfacing with. Yeah. I never used this, so I don't know. Okay, so let's just summary. Like the I2C is just I2C and SPI are just like protocols. UART and serial, asynchronous point-to-point communication, TX/RX values for debugging, logging, GPS Bluetooth modules, speeds up from 9600 baud up to Mbps. So this is like the serial protocol, so you know, like USB and stuff like that, I guess. So yeah, you have like transmitter and receiver. Together these form the bread and butter of the embedded element. You cross-compile code, talk to peripherals via memory mapped registers, and communicate outside the world using I2C, SPI, or UART. Okay, there you go. We have, now you can assume that we know these things. Let's continue. Other resources. If you're unfamiliar with anything mentioned above, if you want more information about a specific topic mentioned in this book, you might find some of these resources helpful. Rust book, Rust embedded. What is this? Discovery book. Discover the world of microcontrollers using Rust. There are currently 3 versions of this book. Okay. Latest version. Let's have a look at what is this. Damn, there are a lot of... God damn, there are a lot of resources on embedded Rust. Okay, interesting. I'm not gonna get into... This looks a bit advanced. But let's just take a peek into it. Timers. Inputs and outputs. Registers. What is this? Okay, anyways, this looks a bit advanced. Yeah, whatever. Rust embedded Rust bookshelf. You can find several other resources. Oh yeah, discovery. If you have never done any embedded program, this book might be a better start. I don't know, maybe. You can find several other resources providing Rust's embedded working group. Embed Nomicon. These are too advanced. Embedded frequently asked questions. Comprehensive Rust, bare metal, interrupts. SPI, UART, or RS232. These are like protocols. Okay, nice page. I like this page. Maybe we should just get into this before moving on with this book. Someone made a Rust embedded drone on Reddit. Yeah. Really crazy projects. Does Rust support my device? Short answer. Rust Composer supports cross-compiling these embedded architectures. Cortex, whatever. Rust also supports code generation. Long answer. We can talk about support on different levels. Architecture support. Okay, cool. Create ecosystem support. When will Rust support the AVR architecture? Okay, this is not interesting. When will Rust support Xtensa? LLVM, okay. I think, is this like up to date? Because there's like a Xtensa target now. My embedded Rust program is too big. Sometimes I get questions like, yeah. Cargo size? Is this like packaged actually? Cargo size. No, cargo bin utils. Cargo bin utils. Cargo subcommands invoked LLVM tool shipped with Rust toolchain. This is kind of outdated. Like they don't maintain. Are they maintaining this? I don't know. I'll just watch the releases. Cargo size seems pretty good. Cargo size bin app. Okay, let me actually install it, dude. Let me just install it. I'm gonna build this. Cargo bin utils. Alright, let's build a package. Texture, okay. Text RO data and data will occupy flash and ROM. PSS and data will occupy RAM. Okay, these are RAM, these are flash. Try to follow the book, my program won't flash. Oh shit, what's going on? Okay, I guess I need to compile this from source. What do we have in here? So many different crates, man. Okay, cargo build. Hopefully it will build. I'm really curious about the size of my embedded program. Okay, this is a good page. I like this page. So yeah, there you go. How to use this book. This book generally seems that you're reading it front to back. Later chapters build on concepts in earlier chapters, and earlier chapters may not dig into details on a topic. STM32F3 Discovery Development Board from ST Microelectronics for the majority of the examples contained within. Alright, let's see what this thing is about. Alright, STM32. How much RAM or like CPU do we have on this? Am I blind? I don't see it. Memory. Memory. Okay, 72 MHz CPU, 48 kilobytes of RAM. Alright, that's cool. Okay, that actually builds. So cargo install path. I'm gonna also pull up my project tweetar firmware. I'm so curious how big is my program. Okay, there you go. So let's go on with the hardware section. Okay, there you go. A single core ARM Cortex processor hardware support for single precision floating point operations and a maximum clock frequency of 72 MHz. 256 kilobyte of flash memory, 48 kilobytes of RAM, a variety of integrated peripherals such as I2C, SPI, and USART, general purpose input-output, GPIO, and other pins. Yeah, I can see that. USB interface accessible through the USB port label USB user. USB user, okay. Accelerometer, magnetometer. What is that? Gyroscope. Oh, it has a lot of things. Okay, cool. No STD. No STD Rust environment. The term embedded programming is used for a wide range of different classes of programming, ranging from programming 8-bit MCUs like this one, which is a few kilobytes of RAM and ROM, up to systems like Raspberry Pi, and different restrictions, limitations will apply when writing code depending on what kind of target and use case you have. Two general embedded programming classifications. Hosted environments. These kinds of environments are close to a normal PC environment. What this means is that you are provided with a system interface, a POSIX that provides you with primitives to interact with various systems such as file systems and so on. Standard libraries turn usually depend on these primitives to implement their functionality. You may also have some sort of sysrd and restrictions on RAM usage, so this is like Raspberry Pi. Bare metal. In bare metal environment, no code has been loaded before your program. This versus Arduino or Pi. depends on your use case, bro. What are you gonna build? Without the software provided by an OS, we cannot load a standard library. Instead, the program along with crates it can only use the hardware to run. So bare metal. To prevent Rust from loading the standard library, use no STD. The platform agnostic parts of the standard library are available through libcore. So this is yeah, you can like load certain parts of the standard library. I guess. Or yeah, you can just, yeah. libstd runtime. As mentioned before, using libstd requires some sort of system integration, but this is not only because libstd is just providing a common way of accessing OS abstractions. It also provides a runtime. This runtime, among other things, takes care of setting up stack overflow protection, processing command line arguments, spawning the main thread before a program's main function is invoked. This runtime also won't be available in a noSTD environment. Summary. noSTD is a crate level attribute that indicates that the crate will link to the core crate instead of the STD crate. The libcore crate in turn is a platform agnostic subset of the STD crate, which makes no assumptions about the system the program will run on. Okay. So heap dynamic memory, we don't have it on, what is this, usually, yeah, use the alloc crate and suitable allocator, use collections crate, hash, okay, so these are like exceptions, I guess. You have heap available on noSTD and STD, but you gotta use the alloc crate and an allocator. Collections are kind of available. Stack overflow protection is not available on noSTD. Runs init code before main is not available on noSTD. libstd is not there. Okay, that's a good summary. Alright. Tooling. Let's see if this thing installed. Okay. We have cargo size now. Let's see. Cargo size. Is it running? What is it doing now? It's absolutely no indicator of what's going on here. Cargo size, cargo read object, cargo strip. Okay, it's building. Let's see the size of my program. Okay, could not find tool size. LLVM tools. Okay, we're installing LLVM tools. Toolchain ESP does not support components. Damn. How am I supposed to use LLVM stuff then? This toolchain file is not installed. I don't think this is related to me. Rustlang is on toolchain or ESP microcontrollers. Okay, I don't know what's going on and I'm not sure if I want to debug this now. Cargo bin utils. ESP does not support components, or maybe I should look for this first error message. Could not find tool size. Okay, whatever. What happens like if I run this on on like a typical Rust app on a binary. Let me just install it for the GNU target at least. Alright, moving on. Dealing with microcontrollers involves using several different tools, as we'll be dealing with an architecture different than your laptops, and we'll have to run and debug programs on a remote device. We'll use these things. Cargo bin utils, cargo generate. Okay, these are like... Yeah, okay, I'm just gonna skip these things. The advantage of using these tools over GNU bin utils is installing LLVM tools is the same on command installation. Tools like Object-DOM support all the architectures that Rust supports, so bit of work. Yeah, I can see the size of this thing, but it doesn't work for my ESP firmware. I don't know, maybe it's not supported really. I have no idea. Maybe we should look into the ESP book for that, but anyways. QEMU is an emulator. In this case, we use the variant that can fully emulate ARM systems. It's not really relevant to me. I'm not gonna emulate anything, but yeah. Debugging embedded systems in Rust. Okay. ProbeRS. ProbeRS is a modern Rust-focused software designed to work with debuggers in embedded systems. I think I packaged this one, ProbeRS. Did I package it? Or is it like... Is it in the AUR? ProbeRS. ProbeRS. For some reason, it doesn't load for me, like... Okay. I should move this to the repos. Wait, which ProbeRS? Okay, I installed it from AUR. I think I'm gonna move this to the official repos later. It deserves to be there. Okay, that's for debugging stuff. OpenOCD. Debuggers. Debuggers know how to interact with the memory and so on. GDB probes. A hardware probe is a device used in development and debugging of embedded systems to facilitate communication between a host computer and a target embedded device. It typically supports protocols like JTAG or SWD, enabling it to program, debug, and analyze the microcontroller and microprocessor on the embedded system. Hardware probes are crucial for developers to set breakpoints. What does it look like? Like, what is that? Why do we have an Arch wiki for that? It's a Perl program. Okay, this is not what we need. Rusty probe. What the hell is that? I'm learning new tools, man. This is an open hardware probe for the serial wire debug and JTAG. This is the probe. I'm just gonna start. It looks cool. Where to buy? The probe is available in the ProbeRS shop. They have a shop? Damn. Okay, I'm getting one, bro. I'm getting one. Okay, 404. They have a shop, man, but it's like 404. Damn it. Catalog. Home. Interesting. This hasn't been updated for some time though. Anyways, ST-Link, J-Link, MC. So these are like debuggers. Okay, installation. It's like adding targets and stuff like that, and installing cargo bin utils and so on. Anyways. Alright, so doing some debugging stuff there. Anyways, getting started. We'll walk you through the process of writing, building, flashing, and debugging embedded programs. Kimu. So there's a quick start template here. Let's see how it looks like. It's archived. Progress DFMT flip link. What is flip link? Flips the memory layout of embedded programs to protect against stack overflows. BaM and Rust programs may not be memory safe in the presence of a stack overflows. For example, this is the case for Rust programs based on Cortex-M RT crate. So this is like flipping the memory layout. Usage. You just use flip link instead of the default linker, okay. Very interesting. Very interesting stuff. I'm gonna start this too. Let's see if this is packaged. Yeah, it's in the extra repository. Flip link. I'm gonna watch the releases for this as well. Okay. I was taking a look at this thing. Okay, progress. Add a HAL as a dependency. Hardware abstraction layer. Okay, what is that? Let's ask ChatGPT. Where is it? Where's my ChatGPT, bro? Okay. What is this? Software layer that hides the low-level details of the hardware and exposes a clean, consistent API for developers. Provides functions like GPIO write instead of requiring you to know which bit in which memory address to flip. Separates application logic from hardware specific details. Makes code portable across different microcontrollers or boards with minimal changes. Why it matters: without HAL you directly manipulate registers, your code is tied to one chip or vendor. With HAL, the HAL handles those registers internally while you program against the higher level functions. Examples: STM32 HAL, functions for GPIO, I2C, SPI timers. Okay, got it. Analogy: think of it like a universal remote control. Okay, got it. Cool. Let's go back here. So you add your HAL here, import it, get a linker script and run. Nice template, bro. A lot of things in here. What is DFMT though? DFMT. Efficient deferred formatting or logging on embedded applications. Deformat, deferred formatting, logging framework. How does it work though? They have a GitHub sponsors. What is Neuralink? Seems like a nice stuff are happening in here. Do they have sponsors? Oh yeah, they have sponsors. They have hella sponsors, bro. Oh, they have a goal of $5,000 per month. Okay, I guess good luck with that. Okay, I'm just gonna take a look at the code real quick. Hello, let's take a look at this. Just curious about these files, man. Runner progress, run chip. Okay. Rust flags. Somebody's texting me. What is going on? Just Twitter DMs. Okay, so I have an idea of how this works now. Program overview. For convenience, here are the most important parts of the source code. So we have the no std marker, of course, no main, cortex entry. No std indicates that the program will not link to the standard crate. No main indicates that this program won't use a standard main. This crate provides a panic handler that defines the panicking behavior of the program. We will cover this more in the panicking chapter. Entry is an attribute provided by this cortex crate as marked entry point. Okay, cross compiling. Not really interested in that. Now we have a non-native ELF binary. We can inspect using cargo bin utils. ELF headers confirm that this is an ARM binary. Cargo size. Cargo size. Wait. Cargo size and A dash A. What is that doing? Actually, don't have this. Okay, this is another. This is just the. I think apps, like apps parameter or something. I don't know. Like it belongs to the app. You know what I mean? These are like the linker sections. Constant values like strings, data, statically allocated variables. Those initial values are not zero. Vector table. I mean, cargo size does not work with my ESP32 app. I'll look into why. Okay, it's just running it in the QEMU environment. Debugging. Critical to embedded download. Debugging an embedded device involves remote debugging, as the program that we want to debug won't be running on the machine that's running the debugger program. Wait, want to debug won't be running on the machine that's running the debugger program. Okay. Remote debugging involves a client and a server. In QEMU setup, the client will be the GDB process and the server will be the QEMU process. Interesting. So this is like running a debugger inside of the QEMU and you just connect to it from outside, I guess. That's how it works. Okay. Okay, moving on. Hardware. By now you should be somewhat familiar with the tooling and development process. In this section we'll switch to real hardware. The process will remain largely the same. Let's dive in. So we used Kimu. I mean, I just like skimmed over it, but yeah, I got what I needed from that section. So yeah, let's just move on. Know your hardware. There's an ARM core included in FPU. Okay, configuring. Okay, just setting the target here. Second step is enter the memory region information into the memory X file. Okay, you gotta edit some file for that. Interesting. Okay, debugging the actual hardware. How does that work? Debugging will look a bit different. In fact, the first step can look different depending on the target device. Open OCD to connect the SD link. Open OCD. We also have that thing packaged. Wait, let me just run this here. Flip link. I'm just gonna adopt this package later. Open OCD. Oh, so many maintainers on this one. Repository. Oh, they have they're not using GitHub. That's kind of sad. Anyways, you gotta do some tweaks on that, and this works, I guess. Okay, memory mapped registers. Embedded systems can only get so far by executing normal Rust code and moving data around in RAM. If you want to get any information into or out of our system, be that blinking LED, detecting a button press, or communicating with an off-chip peripheral on some sort of bus, we're going to have to dip into the world of peripherals and their memory mapped registers. This is interesting. You may well find the code that you need to access the peripherals in your microcontroller has already been written at one of these following levels: board crate, hall crate, microarchitecture crate. High level of abstraction, low level of abstraction. This is a nice graph. Sort of crate handles any useful routines common to the processor core your microcontroller is using, as well as any peripherals that are common to all microcontrollers that use that particular type of processor core. So this is doing that. Peripheral access crate pack. This sort of crate is a thin wrapper over the various memory wrapper registers defined for a particular part number of microcontroller you are using. Hall crate. Okay, this is where is it? Here. So Hall. These crates offer a more user-friendly API for a particular processor, often by implementing some common trace defined in embedded Hall. Okay, this is good because I've seen this around multiple times and I didn't know what this is. Now I know. Okay, this has some traits, and your system or your hardware is basically implementing these traits, and it's like it's for like generalizing the API of the hardware. So yeah, let's see the traits actually. Only contains only blocking traits or the operations done. Okay, so it has some extras here. There's no serial traits in embedded Hall. Instead, use embedded I/O. Design goals. Must erase device-specific details. Neither registers, blocks, nor magic values should appear in the API. Nice. Okay, that's good. So this means that there's no specific hardware involved in the screen. Must be generic within a device and across devices. The API to use a serial interface must be the same regardless of whether the implementation uses Use art1, UART4, peripheral of device, peripheral of another device. So it's like generalizing it. Where possible, must not be tied to a specific asynchronous model. The API should be usable in blocking mode with the features model, with an async await model, or with a callback model. Must be minimal, thus easy to implement and zero cost yet highly composable. People that want higher level of abstraction should prefer to use this HAL rather than re-implement register manipulation code. Serve as a foundation for building an ecosystem of platform agnostic drivers. Here, driver means a library crate that lets a target platform interface with an external device like a digital sensor or wireless transceiver. The advantage of the system is that by writing drivers and generating library to support enormous target platforms. The advantage for application developers is that adopting embedded HAL, they can unlock all these drivers for their platform. Trait methods must be fallible so that they can be used in any possible situation. Nevertheless, HAL implementations can additionally provide infallible versions of the same methods if they can never fail in their platform. This way, generic code can be usable. Fallible abstractions provided here, but platform-specific code can avoid fallibility-related boilerplate if possible. Out of scope, initialization and configuration stuff like ensure the serial interface and that SPI interface are not using the same pins. The HAL will focus on doing I/O. Nice, I like this. So I2C, let's take a look at SPI because that's what I'm using for the display. Blocking SPI master mode traits. Bus versus device. SPI allows sharing a single bus between many SPI devices. The SCK, MOSI, and MISO lines are wired in parallel to all these devices, and each device gets a dedicated chip select line from MCU like this. Okay, SPI bus and SPI device. For driver authors, when implementing a driver, it's crucial to pick the right trait. Okay, let's take a look at some example driver that uses this actually. I think ST7 to 7 something something. So this thing must use this crate, right? Or maybe no. Feature flags. What are the dependencies? Embedded HAL. Yeah, there you go. So let's take a look at the implementation. So draw target. This is from embedded graphics. Wait, how does this actually use it? SPI device. Oh yeah, there you go. So it uses this trait, so SPI device. Okay, I think, yeah, that's cool. Whoever put so much effort into these traits, shout out to them. Really great stuff, like very clean. Okay, I'm gonna take a look at their organization. I'm already following these people. They don't have a sponsors button, which is kind of sad, but anyways. Okay. See chapter on portability for more information on embedded HAL. Board crate. These crates go one step further than HAL crate by pre-configuring various peripherals and GPIO pins to suit a specific developer kit or board they're using. Okay, there are stuff like this. Interesting. Board support. Okay, nice. Yeah, this is like a higher abstraction on top of everything. Microarchitecture crate, where is that? Okay. Read function as an object, writing, modifying, using a HAL crate. This is a bit advanced. Okay, anyways. Semi-hosting. Let's embedded devices do I/O on the host and is mainly used to log messages to the host console. Semi-hosting requires semi or semi-hosting requires a debug session and pretty much nothing else. No extra wires. Super convenient to use. The downside is that it's super slow. Each write operation can take several milliseconds depending on the hardware debugger. Semi-hosting. Program below is the semi-hosting version of Hello World. You'll see Hello World message within the open OCD logs. You need to enable semi-hosting, whatever. This program will block the terminal. Wait, I don't get it. What? Do I/O on the host and mainly used to. So it's like offloading the I/O to do it on my laptop or something. Okay, let's just ask ChatGPT. Where is it? What the hell is semi-hosting? Printing directory, you are writing a flash system. It asks the host to do it. Basically like MCU saying, hey debugger, can you please handle this printf? Your program calls something like printf. The C library rosters a special semi-hosting call. CP executes a special instruction. Catches this breakpoint. The debugger then prints text to your PC's terminal. Debug logging, file I/O, quick prototyping. Slow. Not standalone. Not portable. Okay, so it's like, yeah, it's basically like that. I don't know why that's useful, but okay. Panicking. Panicking is a core part of the Rust language. Built-in operations like indexing are runtime checked for memory safety. When out-of-bounds indexing is attempted, this results in a panic. The standard library panicking is a defined behavior. It unwinds the stack of the panicking thread unless the user opted for aborting the program on panics. When we have no standard library, this is undefined. So you need a panic handler. Okay, got it. Panic abort, panic halt, panic ITM, semi-hosting. A program can pick one of these behaviors simply by linking to the corresponding crate. Interesting. The fact that the panicking behavior is expressed in the source of an application as a single line of code is not only useful as documentation, but can also be used to change the panicking behavior according to the compilation profile. Interesting. Okay, got it. Nice. You can like configure that. One thing that I didn't check is creates IO though. Let's check creates IO. Do we have a panic handler that prints Ferris or like some ASCII art or something to the console? Something fun like that, or are these all just boring stuff? Anyways, I'm just asking for too much at this point. Exceptions. Exceptions and interrupts are hardware mechanism by which the processor handles asynchronous events and fatal errors. I'm not sure this is relevant to me, to be honest. Feels like Java again. I don't like this page. It just reminds me of Java. Interrupts differ from exceptions and variety of ways. Okay, I didn't get it. Like, what is this page saying? What the hell is this talking about? Okay. Feels like Java again, bro. Well, it's, I don't know, like it feels like an interrupt, right? The operations that you use is largely similar and they are also handled by the same interrupt controller. Whereas exceptions are defined by the Cortex-M architecture. Well, we only have it in the Cortex-M, so whatever. So yeah. Set up the peripherals to generate interrupts requests at the desired occasions. Set the desired priority of the interrupt handler and the interrupt controller. Enable the interrupt handler and the interrupt controller. So many interrupting, man. So many interrupts. Let's see. Okay, you just like it's like an annotation and that's all. So IO. To do, cover memory map to IO using registers. Okay, peripherals. Most microcontrollers have more than just CPU, RAM, or flash memory. They contain sections of silicon which are used for interacting with systems outside of the microcontroller, as well as directly and indirectly interacting with their surroundings, like motors and sensors and so on. Alright, these peripherals are useful because they allow a developer to offload processing to them. Okay, if you look at a main circuit board in an old-fashioned home computer from the 1970s, you would expect to see processor, RAM, ROM, and IO controller. Okay. Joined to the processor, those series of parallel threads is known as bus. Data bus. In our embedded microcontrollers, the same principles apply, it's just that everything is packed on to a single piece of silicon. However, unlike graphic cards, which is typically have software API like Vulkan, Stone, and linear and real memory space. God damn. Okay, on desktop system. Alright, you know what I'm gonna do? I'm not gonna read all of this. Just gonna summarize it. Super short. On microcontrollers, there is no virtual memory. The numbers you use on real hardware. Wait, the numbers you use are the real hardware addresses. Okay. The RAM, flash, and peripherals all live in big address space. Writing to a certain weird-looking address like this doesn't touch RAM, it pokes hardware registers. Writing to the UART register address makes the chip send a byte over serial. Basically, talking to hardware equals writing to special memory addresses. Okay, that was it. Just like this section is just yapping a lot, so just thank me later, okay? Whoever watching this live stream, thank me later, guys. I mean, I just like saved you from whatever. Okay, I respect the authors of this book, don't get me wrong, but I'm just lazy. First attempt. Do I really want to learn all of this stuff? Probably not. The borrow checker, this is interesting though. Hardware is basically nothing but mutable global state, which can feel very frightening for a Rust developer. Hardware exists independently from the structure of the code we write. can be modified at any time by the real world. What should our rules be? How can we reliably interact with these peripherals? Always use volatile methods to read or write to peripheral in memory. Okay. In software, we should be able to share any number of read-only accesses to these peripherals. If some software should have read-write access to a peripheral, it should hold only reference to the peripheral. Okay. The last two of these rules sound suspiciously similar to what the borrow checker does already. Imagine if we could pass around ownership of these peripherals or offer immutable or mutable references to them. Well, we can, but for the borrow checker we need to have exactly one instance of each peripheral so Rust can handle this correctly. Well, luckily in the hardware there's only one instance of any given peripheral, but how can we expose that in the structure of our code? Yeah, okay, so this is like, I run into this myself. So if you go to here, I have defined these peripherals, and I actually like this approach where there's like an ownership mechanism for these GPIF pins, so you can only use them once. If you try to use them twice, you get like compiler errors. It says something like this is moved, you cannot use it, and so on. And this is like a safety guarantee. So in the embedded world, they just use the the typical features of Rust to give you safety guarantees, which is something that I like. Why can't we just use global variables? This has a few problems. Yeah, nice and readable, yeah. It's a mutable global variable in Rust. These are always unsafe to interact with. These variables are also visible across your whole program, which means the borrow checker is unable to help you track references and ownership of these variables. How do we use this? Instead of just making a peripheral global variable, we might instead decide to make a structure called peripherals which contain option. Okay, interesting. Yeah, so yeah, basically what this is saying here is that Rust's default features like these mutability rules and so on, they just like play a big role in embedded as well, because this actually maps perfectly to the rules that embedded programming has. So that's pretty cool. Static guarantees. I'm not sure if I'm gonna read all of this now. I might actually jump to the ESP book now, because I think I have enough stuff in my brain already. Design contracts. Portability, this is like HAL. Okay, embedded HAL. Users of the embedded HAL implementation. Driver application. Concurrency. This section might be interesting actually, but I might actually give this a read on my own later. This is just a very deep topic. Collections. Also, this is very interesting. This core is by definition free of memory allocation. This implementation is not available there. You can alloc. So you can use alloc, like you can enable alloc to be able to use vector. To be able to use any collection, you'll first need to use the global allocator attribute. To declare the global allocator, your program will use. This feels like Zig now, because you're using allocators and stuff, like defining, like, you know what I mean, using heap lists. Is this a crate? Heapless static friendly data structures. Changelog. Lips team. Okay. Alright, design patterns. Hulls. Okay, so I'm not developing a hull here. So tips for embedded C developers. Alright, this is for me. No, not really. Preprocessor. In embedded C, it's very common to use a preprocessor for a variety of purposes, such as compile time, selection of code blocks. In Rust, there's no I cannot speak today. In Rust, there's no preprocessor, and so many of these use cases are addressed differently. Compile time, code selection. Well, I'm not a C developer, so I'm just gonna skip these, but yeah. Interoperability. A little Rust with your C. A little C with your Rust, okay. Cool. A little, alright, let's C with your Rust. Unsorted topics. Optimizations, the speed size trade-off. Everyone wants their program to be super fast and super small, but it's usually not possible to have both characteristics. This section discusses the different optimization levels that Rust provides and how they affect the execution time. Oh man, this is very useful. I ran into this before. No optimizations. This is the default vehicle cargo build. Use the development profile. This profile is optimized for debugging, so enables debug information, does not enable any optimizations. At least for bare metal development, debug info is zero cost in the sense that it won't occupy space in flash ROM. So we actually recommend that you enable debug info in the release profile. It is disabled by default. That will let you use breakpoints. Okay. No optimizations is great for debugging because stepping through the code feels like you are executing the program statement by statement. Plus you can print stack variables and functions arguments. The biggest downside of the deb profile is that the resulting binary will be huge and slow. The size is usually more of a problem because unoptimized binaries can occupy dozens of kilobytes of flash, which your target device may not have. The result, your unoptimized binary doesn't fit in your device. Can we have smaller debugger-friendly binaries? Yes, there's a trick. There's a cargo feature named profile overrides. So you just override the profile. Beware that generic code can sometimes optimize alongside of the crate where it's instantiated. I don't know how to read that. Rather than the crate where it's defined. If you create an instance of a generic struct in your application and find that it pulls in code with large footprint, it may be that increasing the optimization level of the relevant dependencies has no effect. Here's an example. Without override and with the override, its text is getting smaller. This has 6 kilobyte reduction in flash usage without any loss in the debuggability of the top crate. If you step into the dependency, then you'll start seeing those very optimized out messages again, but it's usually the case that you want to debug. Okay. Oh, you can use this star thing to select. Okay, nice. Optimize for speed. Level 3 does more vectorization and inlining than level 2. Particularly, you'll see that an opt level equal to or greater than 2 LLVM will unroll loops. Loop unrolling has a rather high cost in terms of flash ROM, but can also halve the execution time. Currently, there's no way to disable loop unrolling, so you can, if you can't afford its cost, you should optimize your program for size. Okay, optimize for size. So these are like S and Z. These names were inherited from the C-Lang LLVM. Z is meant to give the idea that produces small binaries than S. If you want to release binaries, optimize for size. Okay, it's just that. I don't think I care about size at this point. I just want to make fast binaries. So, alright. As of 1.29, these are the inline thresholds that use it, that the different optimization levels use. You should try 225 and 275 and optimizing for size. Okay. Moving on, performing in math functionality. Okay, I think we went through most of these things here, except the static stuff and the borrow checker. No, static stuff and what, concurrency. Yeah, so I skipped those, but whatever, you can read them yourself later. I'm just gonna send a link again. There you go. All right, I'm gonna move on to the ESP book now. This is more relevant to me because I'm using ESP32, so there you go. Introduction. The Rust support for these devices is still a work in progress, and progress is being made rapidly. Because of this, parts of this documentation may be out of date. It's fine. Okay, I already joined ESPRS on Matrix. This book is intended for people with some experience in Rust, also assumes rudimentary knowledge of embedded development and electronics. For those without prior experience, we recommend that you just go to assumption. Okay, assumptions. You're comfortable. I am. You should be familiar with the idioms. Yeah, I think I am. You're comfortable developing embedded systems in other languages. Okay, we already did this thing. If you're unfamiliar or less experienced, okay, Rust programming language book, the embedded Rust book. So this is the thing that we read already, right? Yes, okay, cool. Embedded Rust STD. These two books are also interesting. I'm gonna just open these up. Translations. How to use this book. You just read it front to back. Alright, let's just dive into it. Overview of development approaches. There are following approaches to using Rust on Espresso chips. You can use STD, standard library, or you can use core, no STD for bare metal. Both approaches have their advantages and disadvantages, so you should make a decision based on your project's needs. This chapter contains an overview of two approaches. Okay. See also the comparison of different runtimes in embedded Rust book. Did I? I think, yeah, we read this thing already. Cool. Alright, repository naming convention. In the ESPRS organization, we use the following wording. Repositories starting with ESP are focused on no STD approach. For example, ESP HAL, no STD works on top of bare metal, so ESP is okay, ESP IDF, that's just the STD. They just use this because, I don't know, this is how it is, I guess. STD apart from bare metal also needs an additional layer, which is ESP IDF. Support for expressive products. Okay, let's see. ESP32. I think I have C3. I want to get S3 as well. Rust support for the ESP 8266 series is limited. How does it look like actually? I never heard of that one. I mean, every chip looks like each other. I don't know. They look very similar. Alright, so STD. Espresso provides a C-based development framework called ESP IDF. It has or will have support for all Espresso chips starting with the ESP32. Note that this framework doesn't support the ESP8266. So provides a new lib environment. So what is new lib? The C library intended for use on embedded systems. It's a conglomeration of several parts. It looks so ancient. And why do they have use the Red Hat logo? Is it owned by Red Hat? Download what? Get access. Dude, this is so fucking look at the fucking text on at the top. They have a white background and a yellow foreground, bro. You can tell that it's ancient. They have their own Git. Making sure you're not a robot. Okay. Got the anime girl and everything. That's cool. Okay, they use cgit. Tree. Okay, how old is this? It's actually not that old. Can I clone this actually? Let me just clone it. New lib. Let me just clone this shit. I'm just curious, guys. Give me a second. I gotta check what's popping here. How do I clone this actually? What the fuck? Okay, I just need to clone it from this link. Let me just clone this shit. New lib CYG win. Okay, it's a big repo as well. What does it contain? Okay, just notify me when it's done. Okay, new lib environment with enough functionality to build the Rust standard library on top of it. That's amazing. This is the approach that has been taken to enable STD support on Espresso devices. Is there any info on new lib? And why does it have like a super generic name? New lib. C standard library. Okay, Red Hat. Stable release 8 months ago. Yeah, just like copy all of these things. Dude, this is how I learn new things now. Give me a 20-word summary. There you go. 20 words is more than enough for this. Yeah, okay, whatever. It's just a standard library. Alright. Current support. When using STD, you have access to a lot of features that exist in ESP IDF. Threads, mutex, synchronization, primitives, collections, random number generating sockets. Relevant ESPRS creates embedded SVC, abstraction traits for embedded services. Wi-Fi, so embedded service. So those are like traits, right? Yeah, I guess. I never used this before because I don't have anything to do with Wi-Fi or... I think I use it for logging though. Let me just check. This is still cloning, by the way. Okay, let's check. Tweetar. Am I using this? Embedded the SVC. Nope, I don't use it. I just used graphics and HAL. Okay. ESP IDF service. An implementation of embedded service using ESP IDF drivers. ESP IDF HAL. Embedded HAL in the traits. Says Rust bindings to the ESP IDF development framework gives raw, unsafe access to drivers, Wi-Fi, and more. The aforementioned crates have interdependencies, and this relationship can be seen below. Service. Okay, got it. When you might want to use standard library. Rich functionality. If your embedded system requires lots of functionality like support for networking protocols, file I/O, complex data structures, you likely want to use hosted environment approach because STD libraries provide a wide range of functionality that can be used to build complex applications. Portability. The STD crate provides a standardized set of APIs that can be used across different platforms. So something like, use vector or something, and use vector from STD that exists in many platforms. So I guess that's one example. Rapid development. The STD crate provides a rich set of functionality to applications quickly and efficiently. Okay, cool. So what about no STD? Let's see. This is cloned, by the way. Newlib. What was the command for git fetch or something? No fetch. What was that fetch command, bro? For showing the git summary. Show git summary fetch or something. Dude. Fetch. I think it was one of my packages, but I forgot its name. I'll find it. Fetch. One fetch. Okay, one fetch. Created 26 years ago. No way. Lines of code of what? Almost 500,000. 22,000 commits. Okay, that's crazy. Who's this person? They wrote like the 30% of this library. They must be super productive or super like cracked in the head or something. Okay, I didn't mean that. I'm sorry. Anyways, that was there's a bit of a rabbit hole there. So okay, no STD may be more familiar to embed Rust developers. It doesn't use the STD. Instead, it uses a subset, the core library. It is important to note that no STD uses the Rust core library. Okay, you said that already. As this library is part of the Rust standard library, and no STD crate can compile STD environment. Yeah, cool. Everything is supported, guy. Even myself included. I can run on an OSTD, no problem. No STD, no problem. No. Okay. Cool. Relevant ESPRS crates. ESP HAL, hardware abstraction layer, PAX, Wi-Fi, alloc, println. They have a crate for that, bruh. Why do you have a println crate? Anyways, yeah, the FMT I already saw that. It's kind of cool though. This can do a lot of things. ESP storage, embedded storage traits to access unencrypted flash memory. What? Give me examples. When you might want to use core library. Guys, I'm tired. I'm just gonna drink water, okay? You can just read it yourself. Okay. Direct hardware control. Real-time constraints or time-critical applications. Low latency response times. Actually, I'm thinking of switching to NoSTD for my project because it would be nice to run it faster, you know. Custom requirements. Setting up a development environment. At the moment, Espresso SOC. What is SOC, dude? I've seen this everywhere, but I didn't really look into that. What is SOC? What the fuck is that? What does that stand for, bro? System on chip. CPU, memory, peripherals in one package. They instead of just being a CPU, they CRM and processor. They basically whole system. Okay, got it. They just like refer. They have a fancy name. Two different architectures: RISC-V and Extensa. Both architectures support STD and no-STD approaches. So I use Extensa for my project. To set up the development environment, to the following: install Rust, install requirements based on your targets. RISC-V targets, RISC-V and Extensa. For STD developments, also don't forget to install STD requirements. Okay. Actually, I didn't know I could use RISC-V with my board, but let's see. So I have Rust, RISC-V targets only. RISC-V. Okay, what are we doing here? They're just downloading that. RISC-V32 IMC whatever. So this is for ESP32C2 for STD applications. Extensa targets. So wait, which does it matter which target I'm using? What's the difference? ESP app installs Espresso Rust fork with support for Espresso targets, nightly toolchain for RISC-V targets, LLVM fork with Extensa, GCC toolchain. Okay, interesting. I guess I could port my app to RISC-V. ST development requirements. ESP IDF prerequisites. Python and Git. Linux and macOS, they have different things. LD proxy create, a tool that forwards linkable arguments to the actual linker that is also given as arguments to LD proxy. I don't remember installing that. I think I did. Okay. Flip link. Let's see LD proxy here. Using containers. Alright, interesting. I didn't know you could do that. Writing your own application. Generate from a template. I think I generated my project with a template. ESP generate. ESP IDF template. So this is no STD and this is STD. ESP generator. I never used this before. Maybe I can give it a go. Let's create a project, guys. Let's just go ahead and create a project. So ESP generator. I don't have it installed, of course. I never used it. What? It's not packaged? Are you kidding me? No way, this is... What the hell? This is literally not packaged in Arch. Guys, how is this possible? What the hell? Nah, dude. Maybe it's part of ESP Flash. ESP generate. No way. Dude, we are packaging this shit right now, live. I'm packaging this shit, bruh. There's no way. This is not packaged. ESP generate. No way, nobody packaged this. Not even in AUR. What the hell? Alright, what is the license? What is the license? MIT and Apache. Okay, this releases. Watch the releases. Alright, so new package ESP generate. I'm just gonna copy one of my packages here. Let's copy cargo generate actually. Alright. Oh shit, we have a bunch of stuff going on here. Do we have any features actually? Update informer. I don't need that. Just gonna remove a bunch of stuff here. Alright. ESP generate. Dude, I'm so surprised that nobody actually packaged this thing. It's a pretty cool thing. I know I've seen people use it. It uses Ratatouille as well, I think. Let's see. Yeah, they use Ratatouille. There's a long description for this package, but let's see, what can we do here? Template generation tool to create no SD application. Wait, no STD. Yeah, okay, there we go. It's shorter. I think I'm gonna remove these dependencies for now. Make depends. Cargo. Let's update the package version. When was the latest release actually? I mean, it's not that far ago. Okay, anyway, just build the package. Dude, I'm so surprised, man. Let me just check, just for my sanity. Yeah, it's not packaged by anyone. Okay, I'm packaging it. I am packaging it then. So there you go. Okay, so you just generate a project like that. I think I have C3, right? Let's see, what is this? Yeah, I have C3. Alright, we'll see that in a second. ESP IDF template, I already used this. It's like a, yeah, it's a cool template. Understanding ESP generate. There's toolchain. ESP backtrace. Since we're in a bare metal environment, we need a panic handler that runs if a panic occurs in code. There are a few different crates you can use. Okay, cool. Okay, running the code. Writing no STD applications. Okay, that should failed because of linker optimizations. I'm just gonna disable that actually. Okay, so these are like examples. ESP now. Embassy. I'm actually a bit curious about how difficult it is to use Wi-Fi access point. Seems quite straightforward. Dude, I so badly want to build a Wi-Fi hacking device with this, but I won't. Okay, I won't. I'm resisting. I'm resisting right now. I won't build a hacking device with this. Okay. That is the old me. I moved past those times. All right, I won't do it. Dependency detected, implicitly satisfied. What did I do? Cargo, I included that. Depends cargo, okay, that's weird. Yeah, let's build again. But that's cool, that's cool. That's cool to know that I could build nice hacking tools. Of course, I'm not gonna do it, but it's good to know you could do that. So writing STD applications, the repository STD training. Embedded Rust on expressive training material. Give him a star, bro. Give him a star. Hit that star button. Guys, if you're watching a live stream, please leave a like. Leave a like. 3 likes, 12 people watching and just 3 like. Guys. Hit the like button. Hit the like button. Subscribe. There you go, okay? I mean, come on. Just only 3 likes on the stream? Come on, guys. Hit that like button. Hit the bell, subscribe, give me money. You know how it is. Life is tough out. I'm just joking about the last part, but it would be nice if you hit the like button. Alright, what am I looking at? Embedded Rust trainings for expressive. I2C driver, sensor reading, driving RGB LED. Nice. There's hella examples in here. I like that. Advanced. Oh, of course, I'm straight going into advanced section here. Okay. Tooling. Let's see if this thing is built. Okay. So let me install it. ESP generate. Now we should have it available. CD temp, ESP generate, ESP generate. Sego target chip. My ESP project. Okay, there you go. This is Ratatouille, guys. This project is using Ratatouille. Enable unstable, no. Enable locations, no. Flashing. Yeah, I want to enable this. How can I enable it? Anyways, save and generate. There you go. ESP flash. Alright, it generated a project for us. There you go. Damn, a lot of code. Okay, interesting. I'll take a look at that. By the way, let me just push this to the repo so it's available for you as well. So let me take a final look at the package. I don't know why that took forever to load, but anyways, alright. So commit new package, ESP generate. Yes. I need to tweak something. 1 second. I think it was in package. So alright, I'm just pushing it to the repos for you. Debugging. The extension support is still work in progress. Okay, maybe this is finished. See if they support debugging for Extensa, because I use that. Let me just subscribe to this. Probares. I think I need to move that to the community or like the extra repo as well. So this is now pushed. GDB support and bunch of stuff. Simulating. What is it? VO. What is Walkwe? Walkwe. This is the first time that I'm hearing about that. Rolls the most advanced ESP turns to simulator. Oh, okay. All right. Let's simulate something then. Let's simulate the joke machine. Dude, I should create a simulator for my app here. Damn. But it's Arduino code, which is not nice. Do they support Rust? I hope. Run it. Man, I need Rust support for this. Rust. LinkedIn group. I'm joining that shit, bro. You know that I'm joining that shit. You know I'm a big user of LinkedIn. I'ma just join that. I don't care. Okay, pricing. What the fuck? Rust. No Rust. No Rust, no support. Okay. Walkve user group. Holy shit. What the fuck is this? What is this guy? This guy's building like a... This guy's becoming the Iron Man. Just casually posted on LinkedIn. Wow, dude. Oh my god, dude. That's crazy. I like it. I'ma just support this guy. Insightful. Dude, I'm joining this group. I don't care. This group is so fucking sick, bro. Guys, people are becoming Iron Man in here. Anyways, where's the Rust simulation? Anyways, moving on. Troubleshooting. USB of sys-based projects. Oh yeah, this is what I'm experiencing. Using a 26 megahertz crystal instead of 40 requires modifying the SDK config. Cargo clean, ensure that the changes are properly incorporated into your... I think I need to run cargo clean at some point. You should also prefer using Cargo ESP Flash instead of ESP Flash. Cargo ESP Flash integrates with your project and it will flash the bootloader and partition table that is built for your project instead of the default one. Okay, by the way, in case you're asking, okay, I'm the maintainer of this apparently. What just happened here is ESP generate. Now this should be available. So Paro ESP generate. Okay, I didn't update the repo, so that's not showing up here, but if you search for it, sorry for the flashbang, ESP generate, boom, there you go. Thank me later, guys. If you're doing ESP development, thank me later. Okay, so I'm totally distracted now. Cargo ESP Flash, let's check that. That's wait, that's a different tool. I'm confused now. Cargo ESP Flash, it's part of the ESP Flash package. Oh, okay, wait a minute. Cargo ESP Flash. Oh, it's providing that. Okay, that's fine. Okay, okay. You want to use it, you can specify an appropriate bootloader and partition table using bootloader and partition table. Okay, I need to do that later. Missing LD proxy. If the second stage bootloader reports this error, you likely need to increase the stack size for the main task. How to disable watchdog timers. Okay, I need to disable that too. Yeah, okay. At some point I will just tweak these settings and just run cargo clean. But alright, that's cool. So we have this STD training docs. Training material, it's divided into two workshops, introductory and advanced. Introductory trail will introduce you to basics of embedded development, how to make embedded board interact with the outside world. You can join the ESPRS community. Alright, the board. Okay, preparations. Okay, hardware. I'm just gonna skim through this actually. Software. Okay, at this point we're familiar with these stuff. Workshop repository. STD training. Yeah, this is the thing that I just started. Okay. Hello board. Hardware check. Okay, intro and hardware check. Let me see that actually. Intro. What is this doing? Hardware check. Is it like printing some stuff? Config. Hello world. Connect to a Wi-Fi network. Okay, interesting. Advanced book, common intro. A word on configuration. Use toml config throughout this workshop as a more convenient, secure alternative to putting credentials or other sensitive information directly in the source code. Okay, I just remembered we didn't actually check the code generated by ESP generate. Yeah. Do that. Options. Yeah, walk we. Let's do that as well. At settings for hey helix. Okay, there you go. Create it. Let's check the code real quick. Five gigahertz. Okay, this is just flashing it. What's the difference between ESP flash and cargo? ESP flash. Anyways. Okay, let's see. They have a panic handler here. This creates a default app descriptor required by the bootloader. Okay, interesting. Okay, this looks quite simple. What is diagram though? Oh, this is for the emulation. Oh, okay, linker be nice. Nice. Helpful comments. Intro workshop. Let's see. I think I'm gonna take a look at this later, guys. It's quite a good material though. Oh, this is for the same but no STD. Yeah, this is pretty good. Guys, I'm tired. Cannot go on with this anymore. But let's see. This is using cargo generate with the template repo, right? Just gonna skim through the docs, man. Low level IO. Wait, where's the no STD training? This looks smaller than the STD training. Stack overflow protection with debug assist. Okay. Okay, I think I'm done, guys. This has been a nice trip through the Rust embedded world, but I am tired. Okay, any questions or anything that you want to say to me before I go? I mean, you'll be just lurking this whole live stream. Just everybody was just lurking. I don't know why. Mr. Bones, thanks for tuning in. I don't know why I have so many lurkers in the stream. Guys, okay, show yourself. Who are you? Why are you here? Why are you just watching me and lurking? Friends, come on. Oh man. I'll be back. I think I'll try to do a live stream tomorrow as well. I don't know the topic yet, but maybe just optimizing the code or something like that. I don't know. If anyone is interested in my embedded Rust project, there you go, the repo. Okay. All right. I am out, guys. No one is talking. I did my grinding duty today. Okay, I grinded pretty well. I'm pretty happy how this turned out. So I'm off to another grind. I'll see you in the next one. Okay. Join the Discord, or yeah, if you feel like it, you don't have to. Just send the link to the chat and. Stay with Rust or whatever. I don't know. We don't have a slogan in this channel. Keep grinding, everybody. All right. Don't ever stop. You can stop when you're dead. All right. Anyways, goodbye.